This video is going to focus on factors that influence the strength of solids. That involves charge and their size. And it's also going to take a look at, as I told you before, Claudius's Clapeyron's law, which is going to relate vapor pressure and temperature to characteristics of our liquids and gases. We'll also take a look at phase diagram at the very end. So Coulomb's law examines the energy that's going to be released when two ions interact with one another. This will always be exothermic since the charges of the two ions will be opposite in nature. And the radius is just dealing with the size of the atoms. The larger the atoms are, the smaller this energy will be. As the size increases, they are getting further apart. And so that's going to reduce the amount of interaction that's going to occur between the two ions. The larger the charge, the more electrons that are being transferred, the greater the energy released will be because of that product. So we're going to take a look at several different types of solids in this part of the chapter. We're going to look at ionic solids, solids made from just metal atoms, as well as solids made from noble gas atoms. Molecular solids that are made from nonmetals that are either combined together to make polar or nonpolar molecules. We're going to see some special types of solids, that liquid network covalent solids, things like diamond and graphite. And then we're going to look at solids that don't quite fit into any of the other categories. They're called amorphous solids, and that's because of their ability to kind of shift due to temperature. So we've got here a few solids. Ionic solids are going to be formed using ions. They make up the lattice structure of that solid. In a molecular solid, we see the covalently bonded molecules, the groups of atoms bonded together by covalent bonds, are the main structure behind that lattice. And then in atomic structure, we have individual atoms, which can be both metallic and noble gases. When we have metallic solids, there are not true connections between the two metals, but because there are electrons that the metals are holding on to, there is kind of delocalized sharing. We talked about that a little bit back with bonding, with benzene, that kind of holds those atoms together. In a network covalent solid, we will have true bonds form between the atoms. That's atypical. This is the only one where this happens, but it helps to explain why diamond is so strong, as well as silica. And so these solids connect together to form a true rigid structure. They are not good conductors of heat or electricity because they are made primarily from nonmetal atoms, and they are brittle, with the one exception being diamond. And then in noble gases, we will have solids formed from noble gases at extremely low temperatures, and those form through the London dispersion forces, those intermolecular forces that connect the noble gases to each other. Amorphous solids have disorder, which is why glass can both shrink and expand depending on temperature, which is a really good thing for our windows at home. Because if that was not the case, we would be replacing a lot more windows when we have really cold and really warm temperatures. So what I want you to take a look at with these 8 solids is to identify where these would be classified at. So diamond is one of those special network covalent solids. NBr3 is a polar molecule made of nonmetals. And so that one will be a molecular solid. Hydrogen, H2, is also a molecule. It's not a molecule in the sense that it's different atoms connected together. It is a nonpolar molecule, but it is 2 atoms connected together covalently. So that 2 will be molecular. Magnesium is a metal, and it would be atomic because it's just that metal, but it's metallic as well because it's the metal atoms that are being held together. Potassium chloride is made of ions, and so that's going to be our ionic solid. SF2 is 2 different nonmetals being held together via covalent bonds, so that one is also molecular. Argon is an atom, and so we would see it be atomic, but we will see it be part of the group 18, the noble gas atom solids. And finally we have glucose, C6H12O6, and that one is held together by covalent bonds, and so it too will be molecular. If you need to pause at this point, please do so. So this is the Clapeyron equation, and as I've talked about before, the energy of vaporization is dependent on the strength of those intermolecular forces. And so depending on the ratio between two different temperatures and their associated vapor pressures for a substance, we can determine how large or how small that heat of vaporization should be. When you're using this equation, just like when we used it with our kinetics, we have to have temperatures in Kelvin, and we're going to use a constant of 8.314 since we're wanting to get an energy amount, so we need to use a constant in joules. I'm going to come back and do a couple of examples with that equation after this. I want to talk about state changes now. We've talked about a heating curve before. That was the straight and slope lines I talked about on the previous slide. We're going to talk about phase diagrams at the end of this video, and that's when we talked about in first year chem about normal boiling points and normal melting points, and that's when we have the phase change occur at a pressure of 1 atmosphere. For both of those, that's what the normal pressure would be. And then sublimation is going straight from a solid to a gas. You would need a heat of sublimation to account for the intermolecular forces that have to be broken to change from a solid to a gas. And then the reverse again would be deposition. Supercooling occurs if you cool a liquid down a little bit too quickly and you actually see it stay a liquid below 0 degrees Celsius because you have not given the liquid a chance to rearrange itself in that crystalline structure. It will eventually do that and then go back up to 0 degrees. When you have superheating, you will have a liquid last above 100 degrees Celsius. This is why we tend to put boiling rocks in organic liquids to kind of slow that boiling process down, and it helps to increase that bubbling that needs to occur, the bubbles that have to form within the liquid so that they can vaporize and become a gas. So going back to that Clapeyron equation, this time we're going to take a look and we're going to solve for vapor pressure. We're given what the temperature is for steam at 350 Celsius, and we want to know what pressure would we have to have in order to get it to turn into liquid water at 100 degrees Celsius. We're also given the heat of vaporization, which would be 40.7 kilojoules per mole. Now you might be wondering why we're not being given a pressure for water at 100 degrees Celsius, and that's because at 100 degrees Celsius the pressure of water would need to be 1 atmosphere for it to change from a gas to a liquid. That's going to happen at standard pressure. So that one I do expect you to know that at 100 degrees Celsius you're at a pressure of 1 atmosphere when water changes from a liquid to a gas. So what I've substituted in so far is a second pressure, which is going to be the P2 associated with the 100 degrees Celsius. P1 is the pressure associated with the 350 degrees Celsius. We have our heat of fusion. I converted it from kilojoules to joules so it would cancel out with the joules and our constant. And now I need to turn our temperatures into Kelvin. And I'm going to do that by taking 1 over 623 Kelvin, which will be 273 added to 350, minus 1 over 100 plus 273 Kelvin, which would be 373. This now becomes algebra. Sorry. So I'm just going to simplify the math down, cancel out my units so that I'm left with just units of pressure. And so if I simplify the ratio of the delta H to the R, I get 4,895. And if I simplify the temperatures and take the inverse of both values, I get that I would need to subtract 0.001605. I take that minus 0.002681. And then once I've done that subtraction and multiply that difference by 4,895, I get that that's equal to negative 5.267. I'm sorry, P1 kind of ran off the page. Hold on one second. Okay, hopefully that's a little easier to see now. To get rid of the natural log, we have to take the inverse of it, which is raising both sides by the power of e. That'll cancel out the natural log on the left side. And when we do the math, we'll get that 1 atmosphere over P1 is equal to 0.005159, which is just e to the negative 5.267. And now I want to take the inverse of that value to get P1 by itself. And if you look back up at the top, you're going to see that that is 194 atmospheres. Pretty crazy. If you need to pause, this would be a good time to do so. This will be our last example with Clapeyron's equation. This time we're going to take a look at acetone. We're given the boiling point for acetone. It says normal, so again we're at the pressure of 1 atmosphere. It's 56.5 degrees Celsius. We're told if we go up to 5,300 feet, the atmospheric pressure is 630 torr, and we want to know what temperature of acetone would boil at this elevation. So with Clapeyron's equation, we need to have our pressure, and I forgot to mention this before, I'm sorry. The pressure needs to be in consistent units, and so we're going to take that normal pressure and either convert 630 torr to atmospheres or convert atmospheres into torr. I did the latter, so I set P2 to be the second value that I'm looking for, the one at 5,300 feet, 630 torr, and I set that in ratio to the normal pressure, 760 torr. My delta H of vaporization is going to be turned into joules. I'm going to divide that by my constant, and then my T1 will be my temperature at normal pressure, which is 56.5 converted to Kelvin, 329.7, and then I'm going to be solving for the second temperature, since that's the one associated with the 630 torr. Here comes algebra. So I took the natural log on the left side and got negative 0.1876. I simplified the delta H to R to get 3849 Kelvin. That was the only unit remaining. And then I simplified the 1 divided by 329.7 and left 1 over T2. At this point, you have some choices. You can distribute that 3849 through, or you can divide both sides by 3849. I went ahead and distributed it through, so negative 0.1876 would be equal to the product of the two numbers, 11.674, minus the 3849 divided by T2. You can then subtract 11.674 from both sides, and you'll get that negative 11.8616 is equal to negative 3849 K over T2. You then either need to cross multiply and isolate T2, or you can divide both sides by 3849 with the negative sign and then take the inverse of that value. Whatever way you want to go about the algebra, I do not care. But when all is said and done, you should get a temperature of 324 Kelvin. So it didn't change too much. It did decrease slightly. And when you convert it to Celsius, that would give you a temperature of 51 degrees. If you need to pause, this would be a good time to do so. So the last thing I'm going to talk about really briefly is just reviewing phase diagrams. This is something from first year chem. Just allows us to look at what states we'll find things in at various pressures and temperatures. Critical temperature, critical pressure is one thing I haven't talked about yet this chapter, and that's the end of the liquid gas line. And it's above that temperature and pressure, you can no longer have a liquid, you have to be a gas. And so for water, that would be at a temperature of 374 Celsius and a pressure of 218 atmospheres. Pretty darn high. So this is just to review what a phase diagram looks like. Again, that Y shape, anywhere along the lines connecting the phases, you can have a phase change occur, melting and boiling, subliming and condensing, whatever you want to have happen at those pressures and temperatures. At 1 atmosphere, remember that's our normal melting point, so that's how we got that Tm. That's the temperature at which the solid changes to a liquid at normal pressure. Liquid to a gas is at 1 atmosphere as well, crossing that liquid gas line. There's my critical point, and across is my critical pressure. Going down is my critical temperature. And then the center point is where I have the triple point. At that specific pressure and temperature, I'll have all three phases coexist simultaneously. Notice that the solid gas line and the liquid gas line have positive slopes, whereas the solid liquid line has a negative slope. Just to remind you, that's because ice is less dense than liquid, and it's one of the few solids that is less dense than its liquid state. Here we see carbon dioxide. We see that it is a positive slope, so here the solid phase is more dense than the liquid state. And that is the end of chapters 12 and 13.